Okay, everybody, welcome back. This is our next section of lecture on kinetics 2. And before we get started on this section, I kind of want to talk about what we can do right now. If we wanted to find out the rate of a reaction, we basically conduct an experiment. We take two chemicals together, like chemicals A and B. We make specific initial concentrations of A and B. We react them together, and we figure out what the rate is. And from this type of exercise, we can do this. We can basically figure out the rate law. We can figure out the relationship of A and B to each other. In other words, we can figure out the orders of the reaction, M and N. We can also, from this process here, determine what the rate constant is. But we also know that if we graph this, information, we're probably going to get, if we graph the change in, let's say change in concentration of A with respect from time. If A and B are reactants, we're probably going to end up something like this, with change of concentration versus time. But you notice nowhere in this process are we able to actually determine the concentration of A or B as a function of time. So once you figure out what the rate law expression is, if you integrate the rate law, and the integrate requires the use of calc, and by no means do we expect you to know how to do the calc. If you integrate the rate law, you can actually get an expression that allows you to calculate the concentration as a function of time, right? And then there are different expressions for first order and for a second order rate law expression, right? That basically allow you to know exactly what the concentration is at any time. So it's done a lot different than what we've been doing. It's just that there's another couple equations that are going to come down the pike. And we've already seen some of the graphs. We know that in the first video we talked about what to expect in the different reactions, and that you definitely have to know the shapes of the graphs. In the zero order, first order, and second order, what graph actually makes that graph linear? Whether you're graphing concentration versus time, or you're graphing the natural log of concentration versus time, or 1 over the concentration versus time, is either a zero, first, or second order reaction. So you have to know which one of these graphs gives you a straight line, because it tells you the order of the reaction. All right, so let's get into this. So we're gonna start working through the slides here, and again, we are going to take our rate constant equation and integrate it. All right, so hang on. So in the problem we just looked at, we looked at the problem that had A and B as reactants. So one way we can look at coming up with an equation that gives us the rate, the concentration of A as a function of time is to integrate it. Now we know two things. We know this is the expression that gives us the change in concentration versus time, but we also know the rate is equal to the rate constant for this expression multiplied by the concentration, right? So if I want to integrate it, I basically have to set these two things equal to each other. So, okay, what happens when you integrate this? Well, you get this. So this is the result of performing the integration process on this equation. The natural log of A, the concentration of A at some time t, so this is at some time after t0, all right? So after time t equals 0, this is what the concentration is, minus the concentration at time t equals 0 equals the negative of the rate constant times temperature. So this is concentration at t equals 0, after t equals 0, and that. So this is the equation we use if we have a first order reaction. Now, again, the benefit of this is so we can plot it. If you remember, when you plot a graph of the natural log, I keep writing natural log as an H. So let's just assume that's L and N. Natural log of concentration versus time, we know it gives us a straight line. So this is the equation that allows us to prove this. So where do we get straight line from? If we want a straight line, we need our equation to mimic y equals mx plus b. Right. So if we rearrange this a little bit, so if I rearrange this equation a little bit, I just had to get rid of some of the things that were written below it. The natural log of A, the concentration of A at some time t is going to be our y. And then I get to move some things around. But in order to make this y equals mx plus b, I have to put this term over on this side. So I'm going to have to add this term to both sides. So let me rewrite this with in the kind of the correct order. All right, there we go. So now if I just move the natural log of a0 over, now the natural log of a at sometimes t becomes my y. The the kt is the k is going to be the slope m. The x is going to be the time, because we're going to plot this as concentration, natural log of concentration versus time, and the b is going to be the natural log of the initial concentration. So if I take this and plot it, I'm going to get y and x, and y is going to equal the natural log of a at sometimes t. X is going to be just time, and the slope is going to give me negative k. Right? So it's kind of cool the way this works out. So you got to know this. You got to know the graph. You have to know that the slope is equal to the negative of the rate constant, and you've got to know the equation. Now, this equation is given to you on the exam, but um, it does not tell you, I mean, they're going to give you this equation, but they're not going to tell you that it's only used for first order reactions, right? So it's just something you got to know, all right? All right, let's take a look at solving a problem with this. All right, so let's solve the hypothetical problem that's given in the example down here. So they give us an equation, A goes to form B plus 2D. We want to know three things. We want to know the rate law for the expression, the rate constant, and eventually we want to know what the concentration at 500 seconds is. Now, we just got done talking about first order reactions. So imagine they give you this graph. They give you the graph of the data. And there's a little constant, the chart over here of data, which we're going to use. So the fact that they give you a graph and they tell you that the natural log of concentration versus time is a straight line, it's guaranteed that this is a first order reaction, right? What that will probably do in like a multiple choice question is give you a set of three graphs. They'll give you a graph of just concentration versus time, and if you get a graph, a straight line graph, then you know that it's zero order, or they'll give you 1 over the concentration. If that gives you a straight line, that's going to tell you that it's second order, but we're getting ahead of ourselves. So the fact that the graph is indicative of a first order reaction kind of tells us what a rate law expression is. A rate law expression is going to be. There's only one reactant in the problem, so we know there's no other ingredient we don't have to worry about any other ingredients. So our rate law is simply going to be a rate constant multiplied by the concentration of A. We know it's not going to be to the zero or to the second power, because this graph gives us a straight line with natural log of A. So A just has to be to the first power. So you don't have to write 1 up there, but technically that's the answer for A. Okay, next thing, find the rate constant. Well, this is the point where we're actually going to use our little rate equation, right? Our integrated rate law for a first order reaction. So this is because it's first order, we know to use this equation, and we are going to try to find what the rate constant is. So, I mean, basically, if they're giving you a data table, choose time at t0, right? Um, choose time at t equals 0, and then some other time, so you can end up figuring out what the rate constant is. So if you choose t equals 0 first, what information does that give you? At time t equals 0, this term turns into a 0. At that point, we know what the initial concentration is. Okay, so we know at t equals 0, we go down here, we find out that the initial concentration A0 is equal to 0.02. All right, so we're going to need that for the expression. So I'm trying to solve this expression for the rate constant. So here's what I'm going to do. I'm going to take this equation and start plugging in some numbers. So we need to pick a time other than 0 to get the rate constant. So let's pick this next time down here, which looks like it is um, 5 times 10 seconds, which is just 50 seconds. So let's plug some numbers in. Now we're trying to solve for k. So I suppose we need to get this expression kt to the other side of the equation. So to do that, I'm going to take negative kt and move this expression back over to the other side. Negative kt equals the natural log of a minus the natural log of a0. And then I want to solve for k, so I'm going to divide both sides by time. And if I do this, and then I can technically, to get rid of the negative, I could um, multiply both sides by -1 and end up with k equals the negative of natural log of a minus the natural log of a0. I'm getting sloppy here, divided by time. All right, so that's the equation we're going to use to solve our problem. So let me pause and make some room. Okay, so here's our expression. So we're going to say k equals the negative of. So we're going to pick the concentration at time 50 seconds, which looks like the concentration is 0.017. So we need the natural log of 0.017 minus the natural log of a0, which is 0.02. I'm getting a little bit sloppy in my handwriting here. I am really sorry. And then this whole thing is going to be divided by the time at we're picking t at 50 seconds, or 5 times 10 to the 1, I guess. So 50 seconds. So plug in some numbers and let's get some answers. So when you plug in numbers to the natural logs, you get a lot of negatives. So keep track of your negatives. This gives you natural log of 0.017 gets you negative 4.075. I rounded that last digit, minus, and the answer for natural log of 0.02 is negative 3.912. So when you're done, and you end up making the whole thing negative, then k is equal to these two things divided by 50, and you end up getting, I get 0.00326. And the units in this case, because we're a first order reaction, the units are 1/seconds, or you could say seconds to the -1. So it's pretty cool. Okay, so now this is the rate constant for this expression. So now I can use this to solve the third part of the problem. The third part of the problem is they want to know the concentration at 500 seconds, or 5 times 10 to the 2 seconds. Now, nowhere on the graph, their data table only goes up to 2 times 10 to the 2, or 200 seconds. So this is something that's not on the graph. But now that we have our rate constant, we can figure out what the concentration is going to be at this time. So let me clear some space on the page. Okay, so we want to find the last bit. We want to find concentration of A at, I think that's an at sign, 500 seconds. So what we have to do is take a rate expression, natural log of A equals negative kt plus natural log of a0. Now, we're going to plug numbers in, but eventually we're going to have to undo the log. And remember, to undo a log, if I want to get A, I'm going to have to take E. I'm going to have to take E to the answer. All right, but we'll get there in a bit. So plug some numbers in. Natural log of A is equal to negative. We know what our rate constant is. Negative. Whoops, this isn't a negative. I didn't mean to say that is a negative. It's equal to negative K 0.00326 multiplied by the time that we're talking about, and this is 500 seconds, plus the natural log of a0. Got to put a 0 there. A0 we know is 0.02, so we have natural log of 0.02. All right, so let's get an answer for this. Let's add these two things together and get an answer for natural log of A. Okay, so I did the math on this, and I end up with rate constant times 500 comes out to be, with the negative in front, negative 1.63 plus the natural log of 0.02 is negative 3.912. And when I'm done, I get natural log of A is equal to negative 5.542. Okay, so now to find A, I have to undo a natural log. So to undo a natural log, we just take e to the both sides. So I'm going to take e to the natural log of A is equal to e to the negative 5.542. So get an answer for that. You got to take negative 5.542 and then hit the E button on your calculator. All right. So pause while I do that. So if I hit E to this, I end up getting, and remember on the calculator, it's the E to the X button. So e to the negative 5.542 gets you, and by the way, undoing the natural log gets you A. So A equals, I get 0.039, which is, no, there's another zero in there. Sorry, I looked at the wrong one. 0.0039, which is concentration. So there it is. All right, so I want to do one more problem, just like this, all right? Okay, everyone, I found a new problem for us. So let's try the problem again, right? So let's say here's a set of data. You're looking at the decomposition of hydrogen peroxide. So what we did is we conducted a number of experiments and we plotted the concentration of, we collected data, the concentration of hydrogen peroxide over a function of 24 hours, right? Four readings over 24 hours. And what we did in order to investigate whether it's a first order rate law expression is we plotted the natural log of concentration of hydrogen peroxide as a function of time, and we end up getting a straight line. All right, so this tells us, the fact that it's a straight line tells us that the reaction must be first order. All right, so the rate law for the expression, if there's only one, if there's only one, if there's only one reactant, then the rate law for the expression has to be rate equals rate constant times concentration of hydrogen peroxide. So if it was a if there were actually two ingredients, let's just imagine there's A plus B goes to form something, and they graphed the concentration of A as a function of time, and you got a straight line graph like this. But there were two reactants. It's a possibility that you could have um, it could still be first order with respect to A only, and B could be zero order, while A is first order. So that's a possibility as well. But right now we're assuming with only one reactant that if this is the case, then H2O2 has to be to the first power. So the next thing is get busy, define rate constant. All right. So we know that the expression natural log of A, and the more times you write it, the better you're going to get at it, at remembering what it is. Negative KT plus the natural log of A0. Okay, so you have to find out what A0 is, and A0 is just a matter of finding out what the concentration of hydrogen peroxide is at time t equals 0, and then rearrange this equation to solve for K. So if you remember from last time, we moved the natural log of A 0 to the other side, and then we end up dividing everything by negative t. So in the end, we end up with K equals natural log of A um, minus the natural log of A0 divided by t, and the whole thing, the whole expression, we just put a negative out in front. So I'm going to move over here so we have more room. So the whole thing is negative natural log of, see, whenever I write L, I write an H, and I don't know why I do that. So I apologize. So how do I fix this? It's an L and an N, I guess. The natural log of A. So just pick some time later, right? Why not pick 6 hours, right? You could pick 12, you could pick 18, but let's just pick 6 hours. And at 6 hours, the concentration is 0.5. Now, technically, they give you the natural log here, but let's pretend they didn't give us this side of the column. The natural log of, we're looking at 0.5, is the molarity, minus the natural log of A0, which is 1. And then this whole thing is divided by the time. It looks like we have a time of 6 hours. And there's a negative outside up front. Okay, so pause, and I'll put answers in here for this, and then we'll come up and we'll do the next part. By the way, this is actually a special problem because what happens here is the concentration drops by half, and when you end up going from an initial concentration of 1 to concentration, the natural log of 1 is just 0. So this expression is going to be k equals the negative of natural log of 0.5 is negative 0.693. All right, so it's good. So we get the same number that they got here. Natural log of 0.69, apparently I'm a little bit dyslexic. So let me get rid of that and re-put the right number. 0.693, and that is going to be divided by 6. Okay, so the answer for the rate law expression is going to be negative 0.693 divided by 6, or a rate constant will be 0.115 inverse seconds. Okay, so the next step is to find concentration of hydrogen peroxide at 100 seconds. So let's rearrange and remember our rate law expression. I'm going to keep that there and get rid of everything else. So basically, it's just kind of plugging in numbers at this point. I want to find this, so I know that I need to use my rate constant. So it's going to be a negative 0.115 times t. Now we're going to plug in the time that I'm interested in, 100 seconds. Sorry, it's not 100 seconds. I want to find 100 hours, right? So we'll plug in this times 100 plus the natural log of A0. Now, the natural log of A0, remember this, the initial concentration is 1, so the natural log of 1 is going to be 0. So essentially, it's just going to be this plus 0. So the natural log of A at time t is going to be just equal to negative 0.115 times 100. All right, so let me get an answer for that. Okay, so I get natural log of A equals negative 11.5. And now I have to undo the natural log to get what A is. So I'm going to take e to the both sides. So e to the negative 11.5 gives me, so the e to the natural log of A gives me A equals, and this is a small number, 1, I'm going to call it 1.0 times 10 to the negative 5. 1.0, that's a terrible looking 0. 1.0 times 10 to the negative 5 molarity. So after 100 hours, remember this graph only goes up to 24 hours. After 100 hours, the concentration is near nil. But that's a whole cycle of the problem, right? Okay, now let's move on to second order process. Before we go on to second order reactions, I forgot to talk about the concept of half-life. And we kind of saw this in the problem we just did. There is an expression used, and it's not just used in kinetics, it's also used when we're talking about nuclear reactions called half-life. And half-life is literally defined as the time it takes for half of the available molecules to convert into products. If we're talking about the half-life of something like polonium 210, or the half-life of cesium 137, yeah, that's the one I remember. The half-life of this one radioactive isotope of cesium is something like 30 years. And if I was just watching this special on Chernobyl, and cesium is one of the radioactive isotopes that was put into the air, and its half-life is 30 years. So the concept of half-life is like this. If I have 100 grams of cesium, after one half-life, so how do I want to write this? 1t1 half, one half-life, I'm going to have exactly 50 grams of it left, but it's going to take 30 years to do that. And then if I start with 50 grams, after another half-life, I'm going to have 25 grams, and then after, if I start with 25, after another half-life, I have half of 25, which is going to be 12.5 grams, and so on. So The half-life is just, it's kind of a metric. It is a constant used to describe how much time it takes a reactant to decrease by one half. All right. And it's used a lot when it comes to talking about nuclear reactions and nuclear radioactivity and so on. But it can also be used in kinetics problems, especially first order kinetics problems. So let me pause and kind of so let me give you a hypothetical problem. Let's say I've got something I know to be a first order reaction, and I know the rate constant for this reaction is something like, I don't know, how about 0.035, all right? And it's a first order reaction, so I want to find out what is the half-life, all right? What's going to be the half-life for this expression? Well, write down your expression. I know natural log of A equals negative KT plus the natural log of A0. So this is all the information I've been giving you in the problem, is the fact that I know the rate constant. How do I find the half-life? Well, make some assumptions. What actually happens in a half-life? The concentration A0 decreases by one half. So the concentration at some time t later is going to be equal exactly one half of the original concentration. So my recommendation is assume the initial concentration, the initial molarity is 1, and the molarity after one half-life equals 0.5, because those are numbers you can plug directly into this expression right now. So let's do that. Let me erase this and give us some room. And so if we want to solve for time, let's rearrange the equation, okay? Bring this natural log expression over to here, and we're going to divide everything by negative k. All right, so t equals natural log of a at some time t minus natural log of a at time 0. By the way, I'm supposed to be putting the t's and the zeros outside the box, but you know what I'm talking about. And we're going to divide the whole thing by negative k. All right, so t equals, what is the concentration at time t? At time t, we're saying the concentration is dropped by half, so just plug in 0.5. The natural log of 0.5 minus the natural log of the initial, we'll assume it's 1. Now this has a very special meaning. Sorry, I just had to burp. The natural log of 1 is equal to 0, right? So it's kind of cool. So what this works out as, by the way, we have to divide by negative k, and the rate constant for this reaction happens to be negative well, it's positive 0.035, but we have to make it a negative 0.035, all right? Negative 0.035. So what we're going to end up with is just this, the natural log of 0.5. Now, if you remember in the previous problem, the natural log of 0.5 is a specific number. It is equal to 0.693, right? Hold on, let me pause for a second. I have to sneeze. So if you remember in the previous problem, the natural log of 0.5, I said 0.693 before, it's equal to negative 0.693. Well, guess what? If you make this assumption all the time, if you have a first order process and you make this assumption all the time, then that you start with 1 molar and after one half-life you literally end up with 0.5, then you kind of end up with a new equation to describe half-life, right? If you think about this, if you end up with this, then we can kind of break this equation down to the half-life is going to be equal to negative 6.93 divided by, why did I do that? Well, I don't know. How about we just solve the rest of this problem? It's not 6.93. Just give me a second. I don't know what I'm doing right now. I do know what I'm doing, but it's still very, very, very early in the morning. Let's solve the rest of the problem, right? We go back to our marker. We have natural log of 0.5 is negative 0.693 divided by negative 0.035. And for this problem, the half-life is going to be equal to, half-life is 19.8. Now, because I kind of assumed a rate constant, I just kind of pulled this out of nowhere. The rate constant was inverse seconds. That means the half-life is going to have a a unit of seconds. All right. So here's the expression. All right. The You can come up with a single expression for half-life for a first-order reaction. So half-life for a first-order expression, if you hear the beeps, by the way, that it means the teachers have just woken up and have started posting on the Google Hangouts. So let me turn the volume off on my phone. Let me turn the volume off on the computer too, just because it goes off like it's like a machine gun. When the teachers wake up, they start saying good morning to each other. I know. We're kind of corny. Okay, so let's develop an expression for half-life. Um, we end up with this whole expression is t equals, remember the negative that gets kind of put in front of everything that I ended up putting down here. I end up having negative, and then the units for um, negative log of 0.5 or negative 0.693 divided by k. So the expression, the negative negative cancels out, and the half-life for a first order reaction ends up being this. It ends up just being 0.693 divided by rate constant. Now this equation, if I remember correctly, this equation is not given on the AP exam, right? Or it might be given. I don't have the AP equation sheet right in front of me. It's part of the stack of papers that I forgot to bring with me from school, and now I can't get back in the building. But you got to know when you can use this equation for half-life, right? The half-life for a second order reaction is completely different, okay? But it's kind of cool. Hopefully the assumptions that we made here kind of make sense, right? If we're hopefully our discussion on half-life makes sense. So let's take a look at another problem. So here's a problem that was given in the handout. It says basically, which of the following processes has the shorter half-life? Justify your answer. So make sure you have a couple things straight right now. Are these processes first-order reactions? Does the rate law represent a first-order reaction? And the answer is yes. Both of these, if there's no zero up top, if they give you a rate law expression that looked like rate equals k, then, or they said rate equals k times z to the 0 power, you know that it's a zero order reaction, and we can't end up using our half law, or we can't use the first order process for that. So the fact that both of these say something to, we assume to the 1 power, we both know they're first order, so we can end up looking at the half-life expression. So half-life expression, because it does say which one has a shorter half-life. Half-life is just literally 0.693 divided by k. So without even answering the question, if you take a number divided by a big number, it's going to give you a smaller number, right? So you can get an answer pretty quickly, but for the first expression, it's going to be 0.693 divided by 428, and the second one, it's going to be 0.693 divided by 296. So if you end up dividing both of those, you get this. Okay, so the answer for which one has a shorter half-life is the one that has a larger rate constant. All right, now remember, units for rate constant for a first order process are 1 over time. So when you take and find the half-life, you're taking something and dividing it by 1 over time, so the answer is time itself. All right, so this is the half-lives of these two reactions. Okay, so it's pretty cool. So now let's take a look at a second order process, all right, a second order reaction. Okay, so imagine you have a second order process, where in this case the rate, and again this is a reaction where we have A goes to form BC plus D, something like this. So there's only one reactant, or there's two reactants and they're both first order, okay? So we have negative change in concentration of A over time is equal to the rate constant times the concentration of A to the second power, which means it's a second order reaction. Now, if you take this expression and integrate it, and by the way, we're not expecting you to know how to integrate it. If you integrate it, you get this. The integration is 1 divided by the concentration of A at some time t minus 1 divided by the concentration of A at initial time t, or t0, how about that, is equal to rate constant times time. So it's a totally different expression. You definitely get this expression on the AP exam, but they don't tell you that it's used for a second order reaction. All right. So we want to be able to plot this. All right. So we said before that the cool thing about this is you can plot it. So if you move some things around, if I move it around so I can get KT in here, we want to be able to plot. We know for a second order process we can plot 1 over concentration as a function of time. So I need to move this equation around so I have this is my y, this becomes my y, and the t becomes the x. The k is the slope. If I just move this over to make it my y-intercept, 1 over a at time t equals kt plus 1 over a at time 0. So I get my y equals m times x t plus b. 1 over a0 is my y-intercept, right? So it's pretty cool. If you plot this, you get this as a graph. You get a nice straight line, and the slope is equal to k, right? And the y-intercept all the way down here is going to be equal to 1 over a0, 1 divided by a0, right? So it's pretty cool. Um, but so you got to know what this expression is. This graph gives you a straight line expression only for a second order process. And you notice the slope of the graph is different as well, right? So let's go use this equation to solve some problems. Sorry, I turned the microphone back on and then immediately coughed. All right, so here's a typical second order process. So it's not that you're going to have the equation kind of hanging out here, but you are going to know it on your equation sheet. So they give you a chemical reaction, and I don't know, is it first order, is it second order? Let the data be the judge. You can't look at the two and say, oh, it's a second order reaction. Look at the data. So they give you two graphs. They give you a graph of natural log of the concentration of NO2 as a function of time, curvy line, so we know that's our big X. So we know it's not a first order process. We go to 1 over the concentration as a function of time, straight line, cha-ching, that's our process. All right, so we know automatically from this graph we can answer the first question. What is the rate law for this expression? There's only one reactant, so we know the rate law has to be rate equals constant K times NO2 to the second power. Remember, just because there's a 2 in front here does not mean it's a second order process. You have to let the data be the judge, all right? So the first question answered. Now, next question. They give you a data table, and this is the data table where it says the example and rate laws. They want you to find the rate constant. So let's do exactly the same thing. Okay, exactly the same method as we used before for the first order process. So let me get rid of some of this, all right? And we want to find rate constant. So we need to be able to use our expression to find rate constant. Now, there's probably so many ways you can have this equation written down. You have to know how to algebraically manipulate it to get back and forth. But if I'm trying to solve for K, I'm going to move the entire equation over to get it in my favor. So subtract 1 over a0 from both sides and then divide the entire thing by time. So I'm going to get, it's going to be messy, but it'll be okay. 1 over a at time t minus 1 over a at time 0 divided by time. So you have to go to your graph, sorry, not graph, but you have to go to your data table and find out the concentration of A at time 0. And it looks like on your graph at t equals 0, I don't know why I keep calling it graph. At t equals 0, the initial concentration of NO2 is equal to 0.07. So K equals, this thing is minus 1 over 0.07. Now I have to find the concentration at some time later, and you might as well do the very next time. It says t equals 1 times 10 to the 2 seconds. That's 100 seconds. The concentration of NO2 is 0.015. So use those numbers. Use time as 100 seconds and use the concentration 1 over a t is 0.015. And there's your expression, right? I think I just said expression, but I didn't mean to say expression. I meant to say expression, which kind of sounded the same. Anyways, um, take the inverse of 1 over this minus 1 over this divided by 100, and you're going to get the rate constant. So let me do that with my calculator. So when I do this, I get 1 over 0.015 is 66.67 minus 1 over 0.07 is 1 over 0.07 is 14.28, and that whole thing divided by 100 gets me a rate constant of 0.52, which looks to be the answer. Okay, now different scenario on units right now. It's just second order reaction. So remember, rates always has to be there's rate times blah 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 to the blah 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 power. Rate is always molarity per second. So if I am taking a rate constant and multiplying it by essentially a molarity squared, and I have to end up getting units of molarity per second at the end, the rate constant has to have really kind of funky units. And you never know, the AP is evil. They could just ask you a multiple choice question like, what are the units of rate constant for a second order reaction? And you're going to have to tell them 1 over molarity times seconds squared, right? Or it's molarity negative 1 seconds minus 1, right? If that happens to be the particular units for the problem, or it could be hours, right? Depending on it. So it's there it is, right? Okay, now let's do another problem. What about the half-life? Can you have a half-life for a second order reaction? And I'm like, why the heck not, right? How would you find the half order? How would you find the equation for the half-life for a second order reaction? Let's try it. So let's just use this particular expression right here. So we know the half-life is 0.52. So we know sorry, we don't know that. Rate constant is, we just came up with 0.052? Yeah, that's how bad my short-term memory is. The rate constant is 0.52 molarity minus 1 seconds minus 2. And we want to find the half-life. So T1 half. So let's assume exactly the same thing we had before. Let's assume we start with a molarity of 1, and after 1 half-life, we drop to a molarity of 0.5, right? The concentration drops by a half. We want to find what this time is. So take your second order equation and rearrange it to solve for time, right? So second order equation looks like this. Wait for it. So if I take the second order equation and kind of rearrange it, we get this. I get time equals 1 divided by A minus 1 divided by A0. I didn't put square brackets on there, I'm sorry. And this time it's going to be divided by rate constant, K. That is going to be our expression. I think I just said expression again, to get the half-life. All right, so plug some numbers in. Plug in your hypothetical starting with 1 and ending with 0.5. So T1 half equals 1 over initial concentration, 1 over A is our concentration after 1 half-life of 0.5 minus 1 over the initial concentration of 1 divided by our rate constant, which we just happen to choose from the last problem, 0.52. So there's our numbers. 1 divided by 1 is 1. 1 divided by 0.5 is 2. So we end up with half-life equals 2 minus 1 divided by 0.52, or 1 divided by 0.52, which is pretty cool. 1 divided by 0.52 is, so we end up with a half-life of 1.92, and the units here are going to be seconds. Now, it's not always this easy. It's assuming your initial molarity starts at 1, but the actual expression for half-life for a second order process is a little bit different. We can't just make a simplification like this. So the half-life is equal to 1 divided by the rate constant multiplied by the initial concentration. And in this case, the half-life actually depends on the initial concentration of the reaction. Um, the lower the initial concentration, the greater the half-life is going to be. So it's actually a little bit different expression than what we came up with here. But okay, there it is. This is kinetics 2. My best recommendation right now is to do all of the homework problems. Go back to the book. The book, starting on page 587 in the textbook, is actually going over integrated rate laws, and there's a couple great problems that are in there that allows you to work through them. So work, 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 practice, practice, practice. Um, we're going to have our first video chat on Google Hangouts later this week. I don't know what time is good. I'm going to ask the question on. I'm going to ask you guys a question on Google Hangouts to kind of see what time is good, because I want to go over some problems. All right, everybody. See ya.